Q5. We need to find the moment of inertia of rod AB about the axis which goes through one of the ends of this rod. Let's say that the axis goes through point A. Let's imagine placing this rod along the x-axis so that its end A is at the origin and end B is then at a distance 6a from the origin. Now, we'll start with the elemental length, very small bit of this rod of length delta x, distance x from the origin, from the end A of this rod, and we'll try to find the moment of inertia of this elemental particle delta x first. So we'll write down everything for the elemental particle delta x. We're using this method because we know how to find the moment of inertia of the particle. We only need to multiply the mass of the particle by the square of the distance of this particle from the axis. So we need mass of the particle. We can work out the mass of the particle by multiplying its density ρ by its length. Density or mass per unit length is given by the ratio of mass of the rod and its length. So m over 6a gives the density of the rod and the density of the particle. Now, to find the moment of inertia of the particle, we need to multiply the square of the distance of this particle from the axis of rotation, which is x squared, by its mass, which is ρ delta x. Here we are. We worked out the moment of inertia of the elemental particle. Now, consider the whole rod now. The moment of inertia for the whole rod will approximately be the sum of the moments of inertia of these elemental particles when summation goes from end A to end B. Now, let's see what's going to happen when the length of this elemental particle is going to be really, really small. So when delta x is approaching 0. On the one hand, that makes our approximation much more accurate, and we can put an equal sign between the moment of inertia of the whole rod, the actual moment of inertia, and this sum. On the other hand, the limit of this sum when delta x tends to 0 is given by the definite integral, the limits of summation from 0 to 6a, or the limits of integration, and the expression we're going to integrate is x squared ρ delta x. Now we can integrate. The result of integration is ρ x cubed over 3, the limits from 0 to 6a, and that gives us 6 cube a cube ρ over 3. Now, if we substitute the expression for ρ, we'll have 6 cube a cube m over 3 times 6a. We can cancel 1a, which gives us a squared at the top. We can cancel 1, 6 at the top and at the bottom, which gives us 6 squared. 6 squared divided by 3 is 12. So we've got the answer 12a squared m. Sorry, 12m a squared is the moment of inertia of the rod. Let's move on to part B now. Part B, we'll start with I. Now we have to consider the seat, which is made of two rods, OA and OB, each of length 6A, and a circular bit AB. We know the moment of inertia of each rod, so we can just add them up. But we need to find the moment of inertia of a circular bit AB. We have two ways of doing it. We can we know that if a piece of wire is equidistant from an axis, it can be considered as a particle when the moment of inertia about this axis is calculated. So we can use the formula I, the moment of inertia equals mx squared. As before, we used this formula for an elemental particle in part A. In this case, the moment of inertia of part AB will be mass of part AB, which is 3m, multiplied by the radius squared, 6a squared, which gives us 108 ma squared kilogram meter squared. An alternative way is to use the formula from the formula booklet, to use the formula for the hoop from the formula booklet. And the formula for the hoop is the moment of inertia for the hoop of radius r is mass of the hoop multiplied by r squared. Now, as we only have a quarter of a hoop, for part AB, we will need to use a quarter of mr squared, and as the mass of AB is 3m, it means that the mass of the whole hoop will be 4 times 3m, which is 12m, multiplied by the radius, which is 6a squared. Obviously, will give you the same answer, 100 ma squared. So you can use whichever way you prefer in exam. So finally, we need to find the moment of inertia of the seat, which is the moment of inertia of the rod 12 ma squared twice, as we have two rods, and plus the moment of inertia of part AB, 108 ma squared, which gives us 132 ma squared kilograms meters squared.